Welcome back. Today we're going to be learning how to find all of the roots for a polynomial function, whether they are real roots or imaginary roots. And just before we get into that, let's do a little recap on all of the things we've talked about in terms of roots thus far. So roots, remember that's just another name for x-intercepts. So x-intercepts, or we could call them zeros. And those x-intercepts, those zeros, or those factors also end up being the solutions to our related equations. So these are all interchangeable words. I just like to use the word roots because it's the shortest. Anyway, the total number of roots, or the total number of x-intercepts, or the total number of solutions for your equation, the total that's possible is going to be equal to its degree. So the degree is going to dictate the total number of roots or solutions that we're looking for. But only the real roots are going to be visible on a graph, because a graph in x and y axis, a coordinate plane, only shows real numbers. The imaginary roots, those that are imaginary, are going to have to be solved for by hand. And remember, those imaginary roots always come in pairs. Okay, so if, remember, if a number is a root of a function, then we could say that x minus that number is a factor of the function. And it's important to remember that if something is a factor of a function, then it will divide evenly into it. If something is a factor of another thing, it divides evenly, okay? So here's the gist behind finding all roots. If you're given a third, fourth, fifth degree polynomial, and you want to find all of the roots for that polynomial, but only some of them appear on the graph, we saw in the last set of notes how the remainder could be imaginary. Today we're going to figure out how do we find those imaginaries that we can't see on a graph, okay? So we're still going to start with the calculator, or my favorite, Desmos. All right, use your calculator or Desmos to go ahead and find all of the real roots. And then what we can do is use those to divide. If we divide our function by each real root using our synthetic division, our shortcut division, it's going to reduce the degree of our equation or of our function each time we do that. So let's say we have a fourth degree polynomial and we find that two of the roots are real. If we divide once, we get it down to a cubic. We divide again, we get it down to a quadratic. Then that quadratic that's left over is going to contain the imaginary solutions, and we can solve a quadratic using quadratic formula or complete the square. We have other methods for solving, okay? So we're going to divide the function by each real root using synthetic division, and this is going to reduce the degree by 1 each time. All right, and then we're going to solve the remaining quadratic equation, and it shouldn't be factorable, otherwise we would have seen real roots. So when we go to solve the remaining quadratic equation, it could be square root method, it could be quadratic formula, or complete the square. And then the roots, if we wanted, could be used to write the factored form of our function. Okay, so let me show you this actually, this first one, I would argue, we could put it into, I'm going to go ahead, I'll show you. We could type this into Desmos, x minus 7, and we could put in x plus 2, and we could put in x squared plus 16, but I would argue that what the graph is going to show us is something that we probably didn't need the graph for. So if you want to zoom on this, you can, but what's happening here is this graph is only touching twice. It's going to touch once at -2, and we should have seen here that -2 was going to be a solution. It's going to touch again here at 7, and we should have seen here that 7 was going to be a solution. Now there should be 2 more solutions, right? We've got our next to the first, an x to the first, and an x squared. So a degree of 4 tells me there should be 4 solutions. Now I only see 2 on the graph. The other 2 are coming from this. We're not going to get those on the graph. And think about that. I'm going to do this work again in a second, but why are we not seeing this on a graph? Well, x squared plus 16 equal to 0, if we're trying to figure out what zeros that factor out, think about solving this, right? Can x squared equal a -16? On the real number system, no, right? If we were at square root negative 16, we're going to get plus or minus 4i. So those are the two remaining imaginary solutions, okay? So we don't have to do much work on this one because this one's already in factored form, right? Since this is already in factored form, you could go to Desmos, but not really necessary. We should be able to see here that x equals 7 would be a solution, or x equals negative 2 would be a solution. So we would have a root at 7, 0, and a root at negative 2, 0. And then here, we want to figure out what's going to zero that factor out. So if we actually do the work, we could subtract the 16 over and square root both sides. And we can see our other two solutions are plus or minus 4i. So we have 4 solutions, 2 real, 2 imaginary. Let me just organize this a little bit better here. Find all the roots. We have these 2. And they showed up on the graph. And then we have these 2 that did not show up on the graph because they're imaginary. And 4 total because we have 1, 2, 3, 4, degree of 4. Okay? So that wasn't too bad. We didn't actually have to do any division there because it was in factored form. Now if you look at number 2, it's not in factored form, but could we put it in factored form? So could we make number 2 look like number 1? I'm hoping you're saying yes, because if we try to use our grouping process here, the first group, we have an x squared in common, which would leave an x plus 3. The second group has a 25 in common, and that leaves you another x plus 3. So we can factor out an x plus 3. That leaves us an x squared plus 25. So we could actually rewrite this function in factored form using our grouping process. So this means that this graph should have a real root at negative 3, but this is much like the x squared plus 16 we saw a second ago. If we're trying to make x squared plus 25 equals 0, that means we're trying to make x squared equal negative 25, and that's not going to happen with a real number. Right? If we take the square root of negative 25, we're going to get plus or minus 5i. So we have, based on the degree of 3 here, we have 3 roots total. We got 1 real one, so 1 real root, and the other 2 here are the 2 imaginary roots. Again, didn't require any division there because this one we can actually put in factored form using grouping. Now, if you wanted to verify this with your technology, let me just show you. Here, let's put the original in. X cubed plus 3x squared plus 25x plus 70, what did I do there? Plus 75. I swear, guys, this keyboard's too small for my fingers. Okay, so here's our function. It crosses 1 time at negative 3, 0, right? We saw that here, or negative 3, 0. We saw we were going to have that 1 real root, but the degree of 3 means we should have had 3 total. Since only 1 showed up on the graph, those other 2 had to be imaginary. Okay, so those 2 are not so bad. Already in factored form, we don't have to do much work to find all the roots. If we could put it in factored form using one of our factoring processes, again, same thing, we don't need to do a lot of work there, but neither of those options will always be the case. So let me show you what's happening on number 3. So if we look at number 3, this is another situation where we should be able to find all of the roots. But this isn't one we could use our factoring, it's not in factored form, right? So we can't just jump to our solutions. And if I try to use the grouping process, right, there's an x squared in common here, nothing in common here. So right away that grouping process is not going to work for us to be able to factor this. So this is one where we're going to start with the calculator. Let's see what the calculator says about this. So I have an x cubed, and then I have a minus 2x squared plus 5x and 26. Okay, so here's our cubic function that crosses the x-axis one time at negative 2. So from Desmos, we have one real root at x equals -2, or at -2, 0, okay? So the other two roots I know are going to be imaginary. The question is, how do we find those? So remember the concept just with numbers, so you think about this for a second. If I said that 24 was equal to 8, or 24 divided by 8 was equal to 3, that means that 3 times the 8 would take me back to 24, right? This is the same concept we're trying to work on here. If I know that -2 is a root, remember that means that x plus 2 is a factor and that it will divide evenly into my function, right? If -2 is a root, that means that x plus 2 is a factor. Why can't I spell? Is a factor of this function. So if x plus 2 is a factor of the function, that means it's going to divide evenly into the function. So I'm going to use my synthetic division and divide it. Okay, so I have 1x cubed, -2x squared, 5x, and then 26. Then outside of the box, remember we put the opposite of what's in the factor, so we can actually put the root of -2. So we're going to bring the 1 down, multiply -2 times 1 to make -2, add these to make -4, multiply -2 and -4 to make 8, add to make 13, multiply -2 and 13 to make -26, and then add to get a 0. Now it should make sense that we got a 0 there. We had to get a 0 there. We already knew x plus 2 was a factor, so it should have divided evenly. So that 0 was our no remainder, right? That had to happen here. Now, we took an x cubed and divided it down by an x to the first, which means what's left over here is now a quadratic. This is 1x squared minus 4x plus 13. And we're trying to figure out that piece, right? That's the other factor of my function. Right now we could say f of x is equal to, instead of this polynomial, we could say it's a product of this one and this one, right? If, again, 24 divided by 8 is equal to 3, then 3 times the 8 would take me back to 24. If this polynomial divided by x plus 2 is exactly this, that means this one times this one would take me back to this one. So right now our function, we could say, is x plus 2 times x squared minus 4x plus 13. So I already know that this gives me a solution of -2. I just have to figure out what solutions I get from this. What is it that makes x squared minus 4x plus 13 equal 0? Okay, so that's where I'm going to go next with this. So I figured out the factor from Desmos. I used synthetic division to divide it. And let me just fix all this. Okay, so this was a 1, a -4, 13, and a 0. So this now is telling me I have 1x squared minus 4x plus 13, and I want to figure out what's going to make that equal 0, and those are going to be my remaining solutions. So how do I solve that? Well, I've got some options. Can't use the square root method because the 4x is in the middle there. If I wanted to complete the square, I think that would be a good option for this process. If you don't like completing the square, then you could also use the quadratic formula. I would wager that you're more likely to use the quadratic formula, so I'm going to go ahead and do that. Plug 1 in for A, -4 in for B, and then 13 in for C. So x is going to equal -b plus or minus square root of b squared minus 4 times A and C, and that's all going to be divided by 2 times A was 1. So we have negative is a +4, plus or minus under the square root. We have -4 squared minus 4 times A y times C, and that gives me a -36, and it should make sense that we have a negative under the radical. Remember, we were looking for imaginary solutions here. Okay, and then I'll divide it by 2 on the bottom. So this becomes 4 plus or minus the square root of negative 36 is going to be 6i divided by 2. And since those numbers both divide by 2, we can make this 2 plus or minus 3i. So this equation had 3 solutions, and we knew that degree of 3 up here told us we were looking for 3 solutions. Degree 3, 3 solutions, right? So we got one of them here. One of them here from the calculator, and we got the other 2 here using our quadratic formula. Okay, now if we wanted to use those to write this out in fully factored form, we could say that f of x is equal to, remember, negative 2 as an answer made x plus 2 a factor, and if 2 plus 3i is an answer, then x minus 2 minus 3i is a factor, and that's not going to fit. Scooch that over. And if 2 minus 3i is a solution, then x minus 2 plus 3i is our third factor. So that color's really bad, but so down at the bottom there, 2 plus 3i is why I have a negative 2 and a negative 3i, and then 2 minus 3i is why I have a negative 2 and a plus 3i there. Remember, we put the opposites of our solutions into the factors. So this would be the factored form of our function. Okay, so we have found all the roots, one from Desmos, one by hand, and then we use those to write the factored form, which isn't pretty because it's got those complex solutions in there, but there it is. Okay, so let's try that process again. We're trying to find all the roots, and then we're going to use those roots to write the function in factored form. So this time we are looking for 4 total solutions, right? We have a degree of 4, that means 4 solutions. So let's see what we can get on the graph. This is an x to the 4th minus 45 x to the 2nd minus 196, and we have 2 real roots showing up on our graph. So this says from Desmos we have 2 real roots. At x equals -7 and x equals +7. So that means that x plus 7 is a factor, and that means that x minus 7 is a factor. Okay, now there's only 2 solutions. That means the other 2 have to be imaginary solutions. So we're going to have to use division here, and we're going to have to do it twice. So let's take our first root and divide it out. So I'm going to put -7 into my function, and this is 1x to the 4th, no x to the 3rd term in there, so I'm going to put a 0 in for the placeholder, -45x squared, no x to the 1st, 0 for the placeholder, and -196. So this is going to come down, multiply to make -7, add to make -7, multiply to make 49, add to make 4, multiply to make -28, add to make -28, multiply to make 196, add to make 0. And again, a remainder of 0 had to happen there. If we didn't get a remainder of 0, we did something wrong in the work. Okay, we already knew this was a factor and had to divide evenly. So we started with an x to the 4th. This technically now would be an x to the 3rd, but I'm going to divide again this cubic function by my next root. So I'm going to divide now by the -7, by the +7, and take the +7 and divide this down again so I can get down to a quadratic. So if I divide now by positive 7, this comes down, multiply to make 7, add to make 0, multiply we get 0, add we get 4, multiply to get 28, and add to get 0. So again, no remainder. So we started with an x to the 4th, right? This was an x to the 4th. We divided by an x to the 1st, which gave us an x to the 3rd, and we divided by an x to the 1st again, so now we have an x squared left here. So this is 1x squared plus 0x plus 4. We're trying to figure out what makes that last quadratic remaining equation there equal 0. Well, that's not a bad one to solve. If we keep this organized here, if we subtract 4 from both sides, we're looking at an x squared equal to a negative 4. And if we square root both sides, square root, then we see x is going to equal plus or minus 2i, are those imaginary solutions. So we have the factored form for our equation based on those 4 solutions. So f of x can be written as, if negative 7 was a solution, we said x plus 7 would be a factor. If 7 was a solution, x minus 7 is a factor. If positive 2i is a solution, then x minus 2i is a factor. Again, did not give myself space there. And lastly, if negative 2i is a solution, then x plus 2i is a factor. Okay, so there's our factored form, and that came from these 2 real solutions and these 2 imaginary solutions. So the factored form, and let's just consolidate all this. All the roots would be x equals plus or minus 7 and plus or minus 2i. Do that up here? Let me... Oh, not enough space. You get the idea. Okay? So if we have a function that's already in factored form, we shouldn't have to do too much work. Right? Just figure out what makes each of those factors equal 0. Find the zeros. Those are your solutions. Those are your roots. If it's possible to take your function and put it in factored form so that it looks like number 1, then take that route. But if we can't factor, then we're going to use Desmos or use your graphing calculator to find the real roots on the graph and use those to divide down to a quadratic. Once you get a quadratic, we are using the quadratic formula, or using the square root method, or possibly completing the square to find the imaginary roots. Okay, so that does